Hello and welcome to part 3 of the DazToHue tutorial series. In the previous video we exported our character out of DazStudio along with a simple range of motion animation, and it's now time to head over to Houdini and take a look at what the DazToHue assets can do for us. Before leaving DazStudio, however, just take note of the frames per second that the timeline is set to. By default with Daz it's 30 frames per second, and that's what we want to work with. So we just need to make sure that when we do get into Houdini, it's also set to 30 frames per second. So now over in Houdini Indie, what I'm first going to do is create a new project. I'll save it where our tutorial is. I'll call it tutorial. And then I'm immediately going to save the scene. In this case, I'll call it Michael 8 because that's the character we're working with. Now, as I say, we immediately want to change the frames per second. So if you click the global animation options button, by default it's 24 frames per second in Houdini. So we want to change that to 30, apply FPS, and then close. And now we're ready to go. The easiest way to create the DazToHue assets is to use the shelf tool up here. If you don't see the DazToHue shelf, you may just need to click on this plus button, go to shelves, and make sure DazToHue is ticked. Then you can simply click the DazToHue button. It will create a geometry node for us, and if we dive inside that, we will see all of the DazToHue assets. So really now we just need to work from the top down, starting with the import node. We can see the options available on the DazToHue import node. The first is the character name. So I'm going to put in Michael 8. The character name is used when exporting the files out of Houdini. It also gets used in things like the material slots. We'll look at that in a bit more detail later. The next thing it's asking for is the 3 files that we exported out of DazStudio. The first will be our FBX character file. So if I browse to where we put that, it'll be this b_fig FBX. The next file it's wanting is the DTU file. And the last file it needs is the alembic cache. Once all those have been provided, we'll see a side-by-side comparison of the FBX character and the alembic cache. And as we've set our frames per second properly, they should remain in sync as we scrub through the timeline. The next part of the import node deals with deleting any unwanted geometry you may have. It's important that whatever you delete from the FBX character, you also delete from the alembic cache, as we need these 2 point counts to remain the same. There are scenarios where you might want to delete additional geometry. For example, some geographs will be imported with what I call ghost geometry, basically duplicate geometry that you don't need. And this is where you can delete that. We will come back to this section later on because we will want to delete some parts of the eye geometry. But for now, we'll move on. The last section on the import node deals with additional animations. With this section, you can import animations that you have exported out of DazStudio. These are animations that are separate from our range of motion file. These could be things like idle animations or walk cycles or really any animation. And what it will do is retarget those animations onto our new skeleton, export them out at the end of the process so that you can simply import them into Unreal Engine and they should just work straight away. So I went ahead and created a very simple arms up and down animation just as an example. So I'll import that now. You need to give the animations a name, as this is used to name the file when it comes time to exporting. So I'm just going to call this one arms up. Don't worry about this red exclamation mark. I think it's a bug in Houdini. If you simply click on the display flag for any other node and then come back to it, the error goes away. So I'm not too sure what that's about. I need to look into that. So that's it for the import node. Other than the visualize section at the top here, every node has a visualize section and the options will vary depending on what the node is. For the import node, the default visualize option is this side-by-side view. You can also look at just the FBX character, or the skeleton, or the animated skeleton, or just the alembic cache. So the next node is the skeleton node. So if we take a look at that, by default it's showing our FBX character and the skeleton overlaid. If we turn off wire shade, we'll see it a little better. The other visualization options for the skeleton is the joint orientations and the joint hierarchy, which you can't see in the viewport, but we'll show that in a little bit. And then the usual FBX character, skeleton, animation, and alembic cache options. To see the actual joint hierarchy, we can go over to this side panel, click the plus button, and go to New, tab type. Under animation, we can select rig tree. And then up here, we can change it from FBX skin to skeleton. And now we can see a hierarchical view of the character skeleton. The next options specify both the source and target skeletons, and what you select here determines what actions are applied automatically to the skeleton. So source skeleton is Genesis 8.1, which in this case is correct for Michael 8. We also have a Genesis 9 option. If we set it to other, then the node won't know how to perform automatic actions on the skeleton. For example, it won't know how to rename the bones or reorient them. With the target skeleton, the only options we have at the moment are Unreal Engine 5 or other. And similarly, if we select other as the target skeleton, again, the node won't know how to automatically rename the bones because it doesn't know what skeleton we're wanting to target. So it's only by selecting either Genesis 8 or 9 as the source and Unreal Engine 5 as the target that any automatic changes are made to the skeleton. Now at some point, if there is enough demand, I will add earlier versions of Genesis, and I'd also like to add Unity as an option for the target skeleton, but at the moment it's been many years since I've worked with Unity, and I don't know yet if it has a standard skeleton structure in the same way that Unreal Engine tends to. That's something I need to look into. When targeting the Unreal Engine 5 skeleton, we get this additional option to add the missing IK bones to the skeleton. And the last part of the skeleton node deals with performing manual actions on the skeleton bones. So we can reparent bones, rename, reorient, and delete bones. I'll just go through each of these very quickly. So if you hit the plus sign, we select the bone, in this case that we want to reparent. For example, I can reparent the left ball joint. In this case, I'll just pick the calf, and we can see both in the viewport and in the skeleton hierarchy here that has been reparented. Just clear that because we don't want that. Renaming bones works the same way. You select the bone you want to rename. In this case, I'll pick the pelvis, give it a new name, hip for example. You can see that bone has been renamed. Reorienting bones works slightly differently. You still start by picking the bone you want to reorient. In this case, it's useful to visualize joint orientations. Reorienting bones works by applying a pre-rotation to the bone. So typically, you'll be working with values of 90 or negative 90. So for example, if I wanted to rotate this bone 90 degrees around the x-axis, I will just type in 90 for the x vector. We also have the y and z vectors. You can also go the other way by putting in negative 90. You don't have to use 90, but typically you'll be adjusting them by increments of 90 degrees. I'm going to clear that to go back to what we had. And finally, you can delete bones. So again, we hit the plus sign, and we select the bone we want to delete. In this case, again, I'll go with left calf. Now you can see by default, it's not only deleted the calf, but it's deleted every child bone. This is an option you can enable or disable. Typically, you will want to delete the children if you are deleting a bone. You also have the option to just delete the children and not the actual selected bone itself. And you can also invert the whole thing to say delete anything but the selected bone. But it's pretty rare that you'll want to use that. I'll just clear that. And so that's the skeleton that's being created for our Michael 8 character. I don't need the rig tree anymore, so I'll close that. The next node we'll take a look at is the skin node. So again, by default, it displays a side-by-side view of both the FBX and Alembic character. You can see also that it's telling us how many shapes make up each of these characters. So in this case, we have 6 shapes. If we have a look in the visualize section, we now have an option to isolate. This is useful for a lot of things when working with the tools. So in this case, what it's showing us is a number of shapes that are contained in this character. You can see that under the name attribute. So for example, we can isolate and have just the character shape. Likewise, we can have a look at just the shirt. So this section primarily deals with defining or redefining the shapes that make up this character. So at the moment there's 6. We could probably get it down to 2. But again, it's up to your own choice in how you want to work with it. Shapes are broken down into 2 different types. We have the skin shapes. Any skin shapes are included in joint corrective morph calculations. So they will have morph targets generated for them. And prop shapes are excluded from any joint corrective morph generation. They are treated as non-deforming geometry, typically weighted to a single bone. This particular character doesn't have any props, so we'll disregard that section for now. But we will define some skinned geometry shapes. The skin geometry shapes that we set up here can also be used for things like modular character workflows or modular clothing on characters. What you can do when it comes time to export is you can ask it to export a separate file for each shape we define here. So for example, we could export just the character without the clothing and then export the clothing as a separate FBX. As I say, that can be useful if you're going for a character with modular clothing. So what I'm going to do is just define 2 skin geometry shapes. I'm going to call the first one body, and in it I'm going to assign the character itself, the eyelashes, and the tear line. And then I'm going to create another skin geometry, and I'll call this one clothing. I'm going to assign the pants, the shoes, and the shirt. So with that, you can see we've gone from 6 shapes down to 2. And if we have a look under the isolate option, under our name attribute, you can see we have the 2 shapes that we defined. This clean geometry option on the skin node deals with trying to correct any potential issues with the character's mesh. I have seen some scenarios, for example, the centaur character, where once it's imported into Houdini, we do see some isolated points, effectively a ghost of the character's legs in that case, because obviously from the top up it's human, from the bottom down it's this horse character. But you do, as I say, see these isolated points that denote where the character's legs were. I'm not sure why that happens, but this option here to attempt to repair geometry can generally resolve that for us. But for this particular character, it's not needed. So those are all the options on this skin node. Under the hood, the skin node is doing quite a lot, however. You'll notice now our Alembic cache has all the same attributes that our FBX skin had. For example, it's showing the textures, it has the UVs. More importantly, it has the exact same vertex order, which is important when it comes to generating corrective morphs. What's actually happened under the hood is that we have taken the first frame of our Alembic cache and we've turned that into our FBX skin. And because of that, they should be identical in every aspect. So we'll now have a quick look at the occlusion node. So if we set its display flag, the occlusion node deals with deleting parts of the character that are occluded by other parts of the character. Typically this would mean deleting parts of the character's body that are occluded by the clothing. So to demonstrate, we'll enable occlusion culling. And you can see we can have multiple occlusion groups. So I'll create one. And if we specify what we want to be the occluding geometry, so in this case, if I select, for example, the shirt, See the shirt's gone semi-transparent. We can adjust that transparency here. You may also find it better to turn off wire shading. And then the next thing we need to specify is what we are occluding. And you can select either a part of the character. For example, if I just wanted the body, you can see it has occluded the body, but it hasn't captured this part of the arm because that's a separate piece. So rather than that, we can specify, for example, the entire body. Now you can see it's occluding more. It's actually gone a little bit too far. So for this, I'm going to turn back wireframes. It's just easier to see how it works. We have two methods for occluding. The first method is this by volume method. It's difficult to explain how this is working. So what we can do is turn on volumes visualization. And you can see now for the volume method, what it's basically doing is creating this three-dimensional balloon volume around the entire shirt. Any points of the occluded geometry that fall inside this volume will be flagged for deletion. And with the volume method, we get two options. We can effectively inflate it to increase its size, or we can deflate it. The other option, which is difficult to see in this visualization mode, basically it will expand or contract the points that have been flagged for deletion, and it'll do that for each geometry strip. So if we expand it, we will be deleting more of these geometry strips, and if we contract it, we will be bringing some of them back. I think it's actually easier to see that in the normal view. So the way I typically work is to get my volume dilation close to what I want, and then I'll use this expand and contract option, in this case, to bring back some of that neckline. So we want to make sure that you won't be able to see the parts of the body that have been deleted. So that's looking pretty good in this case. Just quickly, the other method is the surface method. It works similarly, except rather than creating a solid three-dimensional volume, it will create a volume just around the surface of the clothing. It won't work too well for this particular shirt, but there are scenarios where this option is better. It tends to work better for clothing that has a lot of holes or that is very concaved in shape. If you imagine, for example, this shirt had a deep V neck, then if we went with the volume method, it's very likely that the parts of the character's chest inside that V shape would also get deleted, whereas with the surface method, that's less likely to happen. Later on in a different tutorial, we can have a bit of an explore of the different clothing occlusion methods. But for now, for this character, we'll stick with the volume method. Let's change back to our default view. So you see now we've deleted the character that's obscured by its shirt. Now we could either create a new occlusion group, or we could add the pants to the existing occlusion group, which is what I'll do in this case. So I'll just select the character's pants. And again, you can see it's turned transparent. Now, because we've added to the occluding group, we just need to finesse the options again. In this case, I think we will just increase the dilation, try and get rid of as much of that leg as we can. And again, we'll use the second option to contract, bring back that neckline. You can also again use the isolate option to just really see what's going on. So if we just select the character's body, you can see now we've pretty much deleted everything that's obscured by the shirt and the pants. For the shoes, I'll create a new group. We'll select the shoes as the occluding geometry. And again, we'll select the character. Actually, as an example, I'll just select the legs. And you can see there, however, that the toenails are a separate piece of geometry. So in this case, I also want to select the toenails. Now, there's a tiny sliver for where the character's leg should be visible. So really now it's a matter, as I say, of just tweaking the sliders to get what you want. In this case, I'm going to I actually don't want to. What I typically do is adjust the dilation to make sure everything that's inside the shoe is gone, and then use this contract option to bring back some of that. Oh, I see what I've done. My apologies, I selected the toenails in the wrong group. I was wondering what was going on there. We'll add the toenails to the right group. Oh, I've done it again. It's not an occluding, it's an occluded piece of geometry. That's better. So now we just finesse these, so that's too far because it's bringing back geometry at the toes there. That looks about right. Drop this back to get that ankle back. One more just in case. Now I just want to check the whole thing. We turn off transparency. One final look. So that's looking pretty good to me. So that's how the occluding node works. Important thing to note, what's happening under the hood, as well as obviously performing all the occlusion operations, it's making sure that both the FBX and dynamic versions of the character remain in sync, so the point count remains the same. You can toggle this occlusion culling on and off, and it will remember your settings. So if we turn it off, you can see our point and primitive count before any occlusions happened. Turn it back on, you can see we've saved somewhere in the order of 24,000 primitives. Next, we'll take a look at the mesh node. Now, the mesh node is all about topology changes. Specifically, you can subdivide the character to create higher poly counts, or you can perform poly reduction operations on the character to reduce poly counts. So if we take a look at that, we can enable it for a start. It works similar to the occlusion node. We can add one or more mesh operations. So we'll have a quick look at subdividing first. It doesn't have many options other than the subdivision depth. What we do need to do is tell it what we want to subdivide. And again, we could do the entire character and its clothing, or we could do just parts of the mesh. When performing subdivision operations, however, it's important that you select a continuous geometry shape or continuous part of a geometry. By that I mean, for example, you wouldn't want to just subdivide part of the character's face, or you will end up with a situation where the vertices don't align anymore. So for example, if I was to just subdivide the lips, you can see now that it's not a connected piece of geometry, and we certainly don't want that. So typically you would either subdivide the entire character, or at least all of the character's body. In this case, I'll just pick the entire character's body. Now obviously do be careful about pushing the depth too high. If you enter a high number, there will be millions of polygons on the screen, and Houdini could potentially crash. In this case, however, I think the character's poly count is high enough, so I'll clear that. Instead, we'll have a look at the poly reduction option. Again, it works by selecting a part of the geometry that you want to poly reduce. In this case, to start with, I'll select the character's clothing as a whole. So by default, it works with this continue reducing within quality tolerance option. And typically that does a pretty good job at reducing the geometry whilst preserving enough detail in areas like these folds. However, you do have a lot of options to play with here, so we can turn that continue reduction off and specify a target percentage ourselves, for example. We can really push it and go down to, say, 4% of the original polygon count. In addition to a percentage, you could specify a particular target for your polygon count. By default, it's 3000, which is a little low for this particular character. You probably want to bump that up to at least 9000, for example. But for now, I will leave it on a percentage, and I'll leave the continue reducing option on. Under the hood, it's using Houdini's poly reduce node, so these options are exactly the same. You can find out more about each of them by looking at Houdini's help for the poly reduction node, or the poly reduce node. But to go through them quickly, you can force it to preserve quads. I don't recommend it. It typically does a worse job than when you allow it to use triangles. Also, given that our ultimate goal is to get this character inside Unreal Engine, Unreal Engine itself will triangulate the geometry on import. So it doesn't really matter if we do that now in Houdini or later on import into Unreal Engine. So I tend to leave it as triangles. The only use original point positions option does exactly what it says. It will prevent the tool from moving any of the points around, but that severely limits how optimized it can perform the poly reduction. So I tend to leave that off. Equalize length is basically about forcing it to try and create more equal sized triangles. So you can see here we have some small triangles, some larger ones. If we were to reduce that a tiny bit, for example, you'll see we now have more equal sized triangles, but again it's at the expense of optimization. I tend to leave that at the default. Preserve features. So the soft edge option is a way of telling it which parts of the geometry we want to preserve more detail in. Likewise, the retain by density attribute. We're going to come back and have a look at both of these options in a later video, but for now I think I'll leave it as is. We have our clothing slightly more optimized than it was. We still have our subdivision 1 character, and we are also occluding parts of the character that are occluded by the clothes. And with that, we've managed to reduce the point and primitive count considerably from what we started out with. Next, we'll take a look at the materials node. The materials node is obviously all about materials. We can see at the top here, currently this character has 42 different materials assigned to it. Now, if we were to import this into Unreal Engine as is, we would end up with 42 material slots for this particular character, which is quite high. Our aim here is to reduce that to a more reasonable number, in the order of 7 to 8 materials for this particular character. The materials node also handles the materials for the eyes, which is a special case. So what I'm going to do, just to help us visualize what's going on, I'm going to select the parts of the character's eyes. So this is cornea, eye moisture, irises, pupils, sclera. I think that's it. Yep. So here you can see the original eye geometry that comes with this DAZ Genesis 8.1 character. Now, in order to get these eyes to look right when the Unreal Engine eye shader is applied, what we want to have is just the overall eye geometry shape. You don't need any of the internal parts of the eye. Once we have that, we just want to apply a front-on UV projection for both eyeballs. Now for Genesis 8 and 8.1 characters, to get this overall eye shape, we just need the eye moisture geometry and the cornea geometry. Both of those combined will give us this overall eye shape. So if I clear isolation and just select those two, our eye moisture and the cornea, you can see now we have that overall eye shape that we want. So what I can do is tell the material node to use that for our eye geometry. And you can see now it's automatically created the appropriate UV projections for that. So if I just bring up UV view, you can see now, if I delete that, that's what it previously was as it comes out of DAZ. And the node will correct that UV mapping. You can adjust the UV scale to suit, although from my own experiments I found a value of 0.8 to work quite well. So that's all there is to getting the eye shader to work. You can now hide the UV layout. Now, some of you might be wondering, well, what do we do about the internal parts of the eye that we're not using? For example, the iris and the sclera. So you'll recall when I was talking about the import node, we had this delete unwanted geometry option. So we're going to use that now to delete those parts of the eye that we don't need. So for the FBX, I'm going to select the sclera. We also don't need the iris. And we also don't need the pupils. You can see now they've been deleted from the FBX character. As I said, we need to make sure these point numbers remain synchronized. So at the moment they don't. What we also need to do is delete them from the Alembic cache. So again, I select the iris, the pupils, sclera. Now our point numbers match again, and we're good to go. So we go back to the materials node. We'll keep working on our character's materials. To unisolate the eyes now. You can see once we've made that change to the eyes, we've gone down to 39 materials from 42. If under the isolate option you have a look at the FBX material name attribute, those are the materials that are still applied to the character. You can see it's created a right and left eye material for us. That was a result of us specifying the eye geometry. What we still need to do is optimize all these other materials. Now how you do this depends very much on how you set up your textures and your materials inside Unreal Engine. For Genesis 8 characters, I typically create a texture atlas with the head, the body, the arms, the legs in a 2x2 grid. So I take those 4K textures and create one 8K texture with the head in the top left, body top right, arms bottom left, and legs bottom right. And we also include the fingernails and the toenails along with the arms and legs. So that's how I typically first go about optimizing my textures for Genesis 8 figures. So to replicate that, if I go to material slots, I'm going to start by creating a body material. So I'll just call it body. I'm going to pick, as I said, my character's head, the body, the arms, and the legs, as well as the fingernails and toenails. So now if we have a look at isolate and we go to FBX material names, we will see now we have this mi_Michael8 body. And that is the material it has created for us, and it's assigned all of this geometry to that material. You'll also see it's prefixed it with this material suffix. I always work with material instances inside Unreal Engine, and I give those an mi_ prefix. If you have a different naming convention, you can change this to whatever you like. So, as I say, I pack those textures into a single 8K texture. And to replicate that, I have this option to change the UVs for this material to a 2x2 grid. What I'll do is bring back the UV layout, and just so we can really see what's going on, I will isolate the characters. Actually, as a shortcut, I can just copy that. Now, bear in mind there isn't much, in fact there isn't any of our character's body left, and there's not much of the legs left, so this isn't a great example of optimizing in this case, but I just wanted to show you the process. At some point, I am really keen to add more UV layout options and also texture baking options here in Houdini, so that we can pretty much just auto pack any part of the geometry and bake the textures across. But, that's a future plan. But for now, as I say, I'm going to pack this to suit the textures I've set up in Unreal Engine for the character's body. So for the top left, I have the character's head. Top right, I always put the character's body. Bottom left will be the arms and also the fingernails. And the bottom right will be the legs and the toenails. Now, if I temporarily come back to our mesh node and disable mesh operations, actually, wrong node, will enable mesh operations. What I'll do is disable occlusion culling. Come back to our material node. That's what it would look like. You could see for a character that hasn't had half of its body deleted. And that's the way I create my textures in Unreal Engine for Genesis 8 characters at least. For Genesis 9 characters, the head and the face are all the one texture. So it's a similar process, other than it also includes the face, not just the head. Now, obviously, the textures now look wrong on that character. That's because we have only changed the UVs. As I say, the DazToHue tools aren't aware of the custom texture I've made for this character inside Unreal Engine. That's another area I'm keen to explore down the track, is how to actually visualize that change here in Houdini. But as our purpose is to get this out of Houdini and into Unreal Engine, I'm not too worried about that sort of thing at the moment. I'm going to hide the UV layout now that we have an idea of what's going on. We'll bring the whole character back, and we'll continue defining our materials. So I need a new material for the face. So I'm going to create another material, call this one face. In that will obviously go our face, as well as things like the ears, the lips, and the eye sockets. I think that's it. If not, we can come back. I'll have a new material for the mouth. In there we'll go mouth, obviously, also the teeth. We'll have a new material for the eyelashes. In there we will pick upper and lower eyelashes. Another material for the tear line, which I just call tear. There we will pick both of those tear line geometry. Now, to check how we're tracking, if we come back to this isolate menu, scroll down to FBX material names, you can see there's a new materials we've created. It's also a good way to just check that we've captured all of the character's body for now that we want. Now I realize I'm missing the eyes, so I'm going to create a new material. I'm going to call it eyes. Now sometimes I create separate materials for the left and right eye, but for this one I'll just create a single eye material for both. In there I'm going to assign our left eye and our right eye. Now all that's left will be materials for the character's clothing. So the shirt, the pants, and the shoes. Now, if this was a production character and we really wanted to bring these materials across in an optimized way, I would go through and create the materials I needed for each part of the clothing. However, because this is just a tutorial, I'm going to cheat and just create a single material for the entire clothing, because I think you get the idea of how this part works. And I'll show you a little shortcut as well. So what we want to do is add all the clothing to this clothing material group. You can see we have HO pants, HO shoes, and hot shirt as a part of the name for all of the clothing. So rather than selecting them all one by one, you can use wildcards in most of the options in DazToHue, especially the options where it's concerning selecting parts of the geometry. So for example, if I put a asterisk and put in ho pants, and then a space, and then ho shoes, and a space, and then, what was it, hot shirt, I think. That should have selected all of our clothing and added it to this clothing material group. And we can check that by having a look at this isolate option again, going down to FBX material name. And you can see now we have just these 7 materials that we've set up. You can also see up here it's gone from 42 materials down to 7. So next is our pose assets node. This is the node that's responsible for generating our joint corrective morphs. So the way this node works is that we have to define our range of motion animation that we created inside of Daz Studio. So this, we basically have to map each frame and the name of each pose onto this node for it to work. Now again, this is a tedious part of the process, but if you land on a range of motion that you're very happy with, similar to how you could save that animation as a pose preset in Daz Studio, you can also save the pose assets options or parameters as a preset inside Houdini. And to do that, you would just click this little cog, save preset, give it a name and tell it where you want to save it to. So we'll do that once we've defined it. And this is where it's handy to sometimes keep, Daz Studio open in the background to make sure you're mapping it correctly. So we'll start with the 3 retargeting poses that we created. It starts at frame 0, and then frame 1 and frame 2. The first of those poses was our Daz pose. And again, you can call these whatever you like. I don't think spaces are allowed, however, in FBX, so probably avoid spaces or any fancy characters. Our second pose was what I'll call our Mani pose. That's the pose aligned to Unreal Engine's Mani skeleton. And the third was just a straight T pose. So again, frame 0 is Daz pose, Mani pose, T pose. And then we get into our joint corrective morphs section. So if we click on Joint Corrective Morphs tab, the generation method, which I'll talk a little bit more about in a minute, but the options are either individual or additive. If you are intending to use a pose driver to drive a particular morph or set of morphs, for example, a shoulder, you probably want to leave it as individual. Individual means that the morph will be calculated based off of the Daz rest pose. The additive method works slightly differently. So if we have a look at the part of our range of motion animation where the calf is bending up through that 155 degrees range, and we've broken it down into steps of 45 degrees, what you can do with the additive method is tell it to calculate each of these steps based on the fact that the previous morph targets had been applied. So basically it's stacking morphs on top of each other. So the first 45 degree bend here will be calculated again off the rest pose. However, the second will be calculated off of that 45 degree rotation pose. Likewise, the next will be calculated off both its previous poses, and so on and so forth. It's a little difficult to explain. It'll become more apparent when we get into Unreal Engine and have a look at applying it, but I'll talk a little bit more about it when we get to the calf section. So now it's a case of just defining each of the joint corrective morph poses that we've set up in Daz. So we started with our foot down at 65 degrees and then up at 45 degrees. So what I'm going to do is create two new JCM groups, and each of those will have a single JCM. Now we are starting at frame 3 for our JCMs. So this will be 3 and 4. The first will be foot bend down 65. The second will be foot bend up 45. The suffix is left for both of these, so remember when I said it's a good idea to just work entirely on the left hand side first and then swap to the right hand side. So that's what we're doing. Both of these morphs are on the left, and then later on, once we've defined all of the left hand side here, we can simply click this mirror from here down button to automatically mirror those definitions, so that will cut down on a bit of time. So we'll keep going. We'll create a new JCM group and a single JCM inside it. This will be on frame 5. This one's going to be our calf bend forward. I believe it was 11 degrees. We can check that. Select the calf. Yes, 11 degrees. Now we're up to the calf bending backwards. So I'm going to create yet another JCM group. This time I'm going to add 4 steps to it. It's going to start at frame 6, be 7, 8, and 9. First one will be calf, bend, back. Make it backward. And it'll be 45 degrees. The next one will be 90. Then it was 135, and finally 155. So in this scenario, we have a single JCM group, and it has 4 JCMs in it. These all relate to the same joint rotation axes. In this case, it's bending backwards. And what I'm going to do here is change the method from the default, which if you look up here was set to, should be set to individual. For this particular group only, I'm going to change it to additive. And again, what that means is it will calculate each of these morphs on the assumption that the previous morphs had been applied. Basically what that means is rather than, as you're morphing through that range of motion, rather than it going up and down, up and down, up and down, as you go through each of these degrees of rotation, it will stack on top of each other. So it'll go from 0 to 1 and stay at 1, and then 0 to 1, 0 to 1, 0 to 1. And as you go back, it will go from 1 to 0 for each of them. Hopefully that makes sense. Now, next, I think we move to our shoulder. So I'll create another JCM group. It's a good idea as well just to periodically check that you're in sync. So frame 9, 155 degrees back for the left calf. So if we go to frame 9, we are indeed 155 degrees back on the left calf. So next we had our shoulder up, 25, actually it's collar. It's collar up, 25 and then 55. So I'm going to add 2 JCMs to this group. This will be frame 10 and 11. I'll call it collar up 25 and collar up 55. This time, even though there are multiple steps in this group, I'm going to leave it as individual for the method, which is the default, just so we can have a look at the difference inside Unreal Engine. I'll create another group for collar down. This only had a single one, and it is down 10 degrees. So collar down 10. It's a good idea to include the rotation degrees in the morph name. I find it helps when you're setting up things like post-process blueprints in Unreal Engine to be able to easily see what the degrees of rotation is. And I think we just had collar back 17 and forward 26. So I need 2 more groups. Each of those just has 1 JCM each. This one will be frame 13 and frame 14. Collar back 26, I think. Nope, back 17. And finally, collar forward 17. And that should be on frame 14 in Daz. Let's just make sure it is. Forward, hang on. Back 17, forward 26, frame 14. Back 17, forward 26. Like I say, it's tedious. It does require some concentration to make sure you don't misdefine any of the JCMs that we're setting up. Now, we need to repeat this for the right-hand side because that's how we set up our range of motion. Now, thankfully, there is an option to speed that up. So you'll see this mirror from here down button. It does exactly what it says. If I was to click it in that first JCM group, it will mirror every JCM group from here below, so from here down. Now, because all these are defined with the left as the suffix, it will flip them to the right, and it will automatically increment the frame numbers for us. So we'll give that a go. We'll click the button. Now if we scroll down, you'll see now at frame 15, we are going through the same range of motion, but this time for the right-hand side. And so just to double check everything's worked properly, frame 26 should be our right collar, forward 26. So in Daz, if we just have a look at frame 26, You can see indeed our right collar is forward 26 degrees. So that's worked. So that's it for setting up this, albeit simple, range of motion. For the joint corrective morphs part anyway, we still have our facial expressions and speech shapes to work with. Before we get to those, just up here, the global naming options. I prefix all my joint corrective morphs in Unreal Engine with JCM. You can change that to whatever you like. And I suffix left and right with just _L or _R, depending on whether it's morph for the left or right hand side of the character. Center, I don't put any suffix. So you can change this to work with any naming convention you use. So now if we have a quick look at our facial morphs and expressions section, again we have the naming suffix. I prefix mine with FAC, F-A-C. You can change that to whatever you want. Now our range of motion file, we put 2 expressions in. From memory we had rage and happy. That was frame 27 and 28. So for facial group, I'm going to add 2 of those. First one will be frame 27, next one 28. First one will be called rage. Next one will be called happy. And that's it for our facial morphs and expressions. And if we have a look at the seams, again, by default, I prefix them with VIS. You can change that to whatever you like. Sorry, just back on facial expressions. Obviously, these are all center. They're not left or right specific. If you were, for example, doing look left or eye left, looking left or in or out, then you can change whether it's left or right. The seams are our speech shapes. Again, we just created 2 of them for an example. That will be frame 29 and 30. So 29, 30. The first one we used was our AA shape. And I believe the last one we used was our F shape. You can scrub through the timeline as you're doing this to kind of remember what we set up, although it's sometimes difficult to tell. Obviously here we are looking at the FBX character, which doesn't have the same level of detail that the Alembic cache character did. Jump back to the side-by-side preview. You can see we've got a lot more of the detail around the mouth and the eyebrows than we get on the linear skinned character without any of the morphs applied. But that's what all of our JCMs are going to fix for us. So we've now finished defining our range of motion for this simple example. Now, as I say, let's assume this is something we want to keep and reuse over and over again. Obviously those parameters are saved with our Houdini scene, but if we want to use them in between scenes, I can click on this little cog and go to Save Preset. I usually save it in my HIP file, which is the Houdini project directory. In this case, I'll call it Michael 8 test. Save that as a preset. Now, if we ever wanted to use that again, we just select the pose asset node, click on the cog again, and we'll see Michael 8 test as one of the presets that we can load onto it. And that'll save us having to specify all of these again. So finally we come to the export node, and not surprisingly this is responsible for exporting all the files out of Houdini ready for importing into Unreal Engine. So the options on the export node, first we have to tell it where we want to export to. So I'm going to export it to our tutorial folder, and I have a subfolder in there just called exports, so I'll select that. And the next is a file name suffix. So this, if you add anything here, it will be appended to the end of every file name that gets outputted. I'm going to leave it blank for this one. This will be our base mesh in Unreal Engine. What I will come back and do is add a LOD level 1, and then when I do that I will add that as a suffix here just to separate the differences, but we'll talk a little bit more about that later. So going through the options for export, export character will export obviously the FBX character with all of its joint corrective morph channels embedded. It will also have our range of motion animation, and it will also have a keyframe for every frame of the range of motion animation driving that particular morph channel. And I'll explain a little bit more about that when we get inside Unreal Engine. If you are exporting the character, you also have the option to export the character's shapes as separate files. So if you'll recall back when I was talking about the skin node, we defined two skin geometry shapes called body and clothing. If we selected this option, then it would export two FBX files in this case, one called body, one called clothing. Both of those would have the morph channels embedded as well as the range of motion animation. And as I said at the time, that's a good option if you're wanting to go down the modular clothing path in particular. Obviously back on that skin node, we could have broken the clothing down into shirt, pants and shoes as separate shapes, and then it would export all of those as separate files. For now, we're just going to leave it with the two shapes. I'm not going to export as separate files on this occasion. Export JCM methods will output a HTML file actually, and it's basically a table with a list of all the joint corrective morphs we defined and the method they were created as, so either individual or additive. It's just a handy reference when you're working in Unreal Engine to be able to refer to what method was used for what morph without you having to have Houdini open and referring back to this. Likewise, export pose asset names will just export the names of all of our pose assets. So that will include these retargeting pose names, all the joint corrective morphs, these facial morphs, and the seams. We'll just put that in a list in a text file, and that is handy if you want to convert our range of motion animation into a pose asset in Unreal Engine, because it allows you to just copy all of the names and paste them into Unreal Engine without having to manually enter the names inside Unreal Engine. It's just a bit of a time saver. We'll have a look at that a little later on. Export additional animations. So if you'll recall, way back when I was talking about the import node, I did import a very simple additional animation of the character's arms just going up and down again. So the export additional animations option will export any of those that we've defined on the import node. It will export them back out, but they will be retargeted onto the character skeleton that we set up on the skeleton node. And they should just work when we import them into Unreal Engine, so we'll see when we get to that. So I'm going to export just that one additional animation I created. Finally, the export Alembic cache option will do just that. It will export our Alembic cache back out of Houdini. This is a useful option if you are wanting to play around with the machine learning deformer tools inside Unreal Engine 5. You will need that Alembic cache as well as our FBX skeleton to get that to work. The Alembic cache isn't exactly the same as it was when it came into Houdini. It has been processed such that, as I say, the vertex counts and positions match exactly between the FBX and Alembic files, and that is critical for getting that machine learning workflow to work. But for this example, I'm not going to be messing around with the ML deformer tool, so I don't need to export the Alembic cache. So now we're ready to export those files. How long the export takes depends on a few things. Obviously, it depends on the mesh density. The more polygons, typically the slower it takes. But it also depends on the various operations we've performed on the mesh along the way. So the occlusion operations and the subdivision or poly reduction operations all have a slight impact on export times. So even though, for example, we are removing a lot of geometry from the original character, those operations need to be performed twice, in fact, one for the FBX and one for the dynamic cache, and they need to be performed for each frame, so it will have a slight impact, but overall this method is far faster than doing any sort of ray casting, which is what other methods I've seen typically use. So with that all set, we will hit the export with selected options button and wait for it to finish exporting. You can see down the bottom here where it says JCM group and pass 1 of 16. That's basically it generating all of the JCM groups. We ended up with 16 JCM groups on our pose assets node. That's what it's working its way through now. So you can see it's pretty quick to get through those. I am hoping I'll be able to optimize things further down the track, but haven't had a chance to look into that yet. So that's finished exporting, and we can see here that it took just over 82 seconds to complete, which I think is pretty reasonable. Obviously, the more pose assets we define and I guess the intensity of the mesh operations we're performing, the slower that will be, but I still think it's quite reasonable in terms of speed. We can close that. So if we have a look at where we exported those to, which was on our desktop, exports, you can see it's exported 4 files for us. We have our FBX character, and as I say, that contains our range of motion animation, all of the morph channels embedded. We also have our retargeted animation, so that simple arms up animation I made. We have our JCM methods, which if I open that, this is what it looks like. It has each of our JCM channel names, the frame number for each, and the method used to generate them. And finally, we have our pose asset names, which is just a list of all of the pose assets we defined on that node. We'll use that in a little bit. So I think we'll leave that there. In the next video, we'll jump into Unreal Engine and have a closer look at those files that it's exported for us. So I'll see you then.